So in this video, I'm going to go over each of the AP practice response questions we've done so far. So first off, they start in Unit 3. So if you want to get back to Unit 3, you have to click on Computer Science Principles at the top, and then you can scroll down. This part's kind of weird. When I open the unit, I have to press continue. If I try to choose the lesson, for some reason it won't find the page. So I'm going to continue and then choose the lesson I want to go to. The first question that came up for us was in Lesson 5 of Unit 3, number 11. That's Lesson 7, number 11. Let me switch over to that one. So here, this was the prompt: capture and paste a program code segment that contains an abstraction you developed individually on your own. The abstraction must integrate mathematical and logical concepts. Explain how your abstraction helped manage the complexity of your program. So this person selected this section here, and it's supposed to make a heart. So we'll just quickly read what they have. The abstraction I have identified draws a heart in the program. The whole program draws a picture with turtle graphics that says I heart CS, where the heart is actually a drawing of a heart shape. Because I'm using the parameterized versions of these turtle functions, it helps manage the complexity of the code. Without the parameters, the drawing is achievable, but would require many more lines of code. For example, the command to arc right 22030, which moves the turtle in a 220-degree arc with a 30-pixel radius, is possible to do with a long series of repeated move forward and turn right commands, possibly hundreds. By using the arc right command, I encapsulate in one line what the code should be doing, rather than having to reason about hundreds of lines of code. So if we scroll down to the rubric, first take a little look at what they put in the rectangle. Row 7 is select code segment as a student-developed abstraction. Responses that use existing abstractions to create a new abstraction, such as creating a list to represent a collection, would earn this point. So I think this student was going for a function here, but they didn't actually take this code and put it into a function. A function could count as an abstraction, especially if the function is used later in the code and there's a reason to do that. So I did not give the student a point for row 7. Basically, the response is an existing abstraction, such as variables, existing control structures, event handlers, APIs. This was the problem. All of these commands are part of Turtle, move forward, turn right. They're kind of trying to use them together, but if they wanted to use them together, they should have made it a function and then explained how they could call it later to draw, for example, multiple hearts in the program. For row 8, explains how the selected abstraction manages the complexity of the program. I did give a point for that. They should not be penalized for explanations of abstractions that were not developed by the student. So any of these things here, arc right, move forward, those are functions with more code inside of them, so they're APIs or developed by the Turtle library. But they do a good job of explaining why arc right is an abstraction, and it's taking a lot of little movements to create an arc and calling them in a simpler way. So I would give a point for row 8, but not for row 7. Next problem we're going to look at is Unit 3, Lesson 8, and it's number 18. So this is a little bit more on managing complexity. So basically, this was the code you wrote to create that undersea picture, and they want you to describe how the function drawFish manages the complexity of the program. It does say, note the requirement that the abstraction integrate mathematical or logical concepts for this practice response. Just write about managing complexity. Okay, so if we look up here, basically those mathematical and logical concepts, anytime you have an equal sign, like you're changing the value of a variable, that would count. If you're doing some sort of an if statement where you're testing mathematically is one thing greater than another thing or equal to, that counts as those mathematical logical concepts. So I actually wrote out a response that I'm going to read. It said, instead of using this code each time I draw a fish, creating a function lets me call this function with one line of code whenever I draw a fish. This makes the code easier to read and hides the details of making the fish in the function. It allows me to make fish of different sizes and colors using one line of code. And just to add to that, I would probably say using parameters in the function, right? Using the size, and then red, green, blue gives those colors for the RGB values. The parameters allow me to make fish of different sizes and colors using one line of code. So that's explaining the complexity instead of using those lines of code every single time. And a function is a really nice thing to use for this part of your create task because usually there's a really nice reason. Other options would be how you use a list that you created, a variable you created throughout your program, anything like that. Those are other examples of abstraction you could use. So the next question is in Unit 3, Lesson 9, and it's number 16. And this is basically just a multiple choice question. Once again, about these student-created abstractions. Looking at the choices, choice A is using a function that's already been created basically by the program. Move to, and then also a random number are functions that are already created within the program. Draw square, also something that's already in the program. This for loop kind of gets there with the variable because the variable is defined and then incremented in order to create this for loop, which is drawing, I think it's a pentagon. I'd have to draw that. I'd have to think about that a little more. But basically, or maybe, no, a star, since it says it. So this is drawing a star. So when you look at this, this variable structure is not really something the student created. This is what a for loop looks like. So that's not the best response. Down here, this is a student-developed abstraction. Function draw square. So this is they've taken different commands that might already be in the program, but they've brought them together into a square. Okay, so rectangle D is a student-developed abstraction. The student used the functions move forward and turn left to create their own function that can be called later. I'm going to switch back over to Unit 5. If I just press code up at the top, that should take me back to the current unit. So I'm going to continue what I'm working on, which is not the right lesson. But then I'm going to go to Lesson 5 in the More menu. Come on. And number 22, I believe is, yeah, that's the AP one. So in this problem, it's kind of that same idea of the abstraction. If I look down here, this one looks like it might be okay. But this onEvent function is something that is already a part of the program, so they didn't really create that function. This score variable, if they had showed defining the score and explaining, you know, I defined the score variable so that I could increment the score when the apple was clicked, but we can't see that variable being defined, right, is an existing abstraction such as variables, existing control structures, event handlers, or APIs. So we can't really see that variable being created. We have a nice mathematical concept here, but once again, it's not really one of those going through a variable, going through a list, how it's created and used, or going through and making your own function. Honestly, making your own function is probably the most straightforward way to talk about an abstraction, but the variables and the lists can work as well. I'm also going to go over one last one that's part of this week's work, but it's connected well to what we're doing. So I'm going to go down to Lesson 9 and look at question 16. So this one is a little bit different. Here you're cutting and pasting a program code segment that implements an algorithm that is fundamental for your program to achieve its intended purpose. So it's still that same idea with an algorithm. This code segment must be an algorithm you developed individually on your own, must include 2 or more algorithms, and must integrate mathematical and/or logical concepts. Describe how each algorithm within your selected algorithm functions independently as well as in combination with others to form a new algorithm that helps to achieve the intended purpose of the program. Now, for this part, they're kind of ignoring that 2 algorithms going into one bigger algorithm piece, and this row, or row 5 point, is just the algorithm being described can utilize existing language functionality or library calls. Response earns the point even if the algorithm was not newly developed. A student's re-implementation of the algorithm to find the minimum value. Mathematical and logical concepts can be a part of the selected algorithm or a part of either of the included algorithms. Okay, so this one, I should have read this part first. Select code segment implements an algorithm that uses mathematical or logical concepts, explains how the selected algorithm functions, describes what the selected algorithm does in relation to the overall purpose of the program. So let's just look at this code. We'll read the person's response. My algorithm controls the login for the app. This piece of my program is important because the data included in my app needs to be secure. The algorithm makes sure only users with the correct password get into the app to use it. So this is decent. It definitely, if you look down here, includes checking for equality. That's a logical piece, so it meets that point. I think they do a good job of explaining the functionality within the whole program. It's important because the data needs to be kept secure. The parts where it's lacking, once again, they're using this on event for their algorithm, and when you use a function, it should really be something that you create, not the on event that's something that's already created. Also, looking at this one, I think there probably should be a little bit more on how. It says what it does. The algorithm makes sure only users with the correct password get into the app to use it. You probably want to explain it a little more. It checks to see if the current password is equal to the saved password, and if it does, then it goes to the home screen. You probably want to give a little bit more how in that description. Okay, and then as I said, those functions do need to be self-defined. And we'll see as you go through this week and especially next week, we're going to kind of see more of that happen, examples, and also functions called within functions and good examples of when to use that.